Good afternoon. I'm Fazil Khan from Aero A. Today I'm going to talk about total potential energy method. The total potential energy is the total potential energy of an elastic body is defined as the sum of total strain energy and the work potential. There's a formula of total potential energy is pi equals to U plus WP, where U is denoted for strain energy and WP is denoted for work potential. So here is the example of total potential energy, how the mass is attached to a string. So total potential energy of the mass equals to mgh, and loss of energy for minus mgy. In We have in both in equilibrium and deflected in equilibrium. So here potential energy of the mass we are using mgh, and loss of energy for minus mgy for both the equations. If instead of weight we had force p, then v equals to minus py in loss of energy in equilibrium. In deflected equilibrium, loss of energy for minus mgy. So deflection can be associated with the loss of potential energy. Is the y is the deflection, h is the height, and m is the potential energy. So here potential energy mass is taken as mg of h minus y in deflected equilibrium. uh, Assuming that the potential energy of the system is zero in the unloaded state, then the loss of potential energy of the load P as it produces a deflection y is Py. Assume mgh equals to 0 or ph equals to 0. So here we are assuming the potential energy of the system is 0 in the unloaded state, and the loss of potential energy of the load P as it produces a deflection y is Py. So the potential energy V of P in the deflected equilibrium state is given by V equals to minus Py. So here there is one more example of total potential energy, where note strain energy in a system. So when strip is attached to a body, where P is load and Y is deflection load, and here is a graph which is showing the total potential energy, complementary energy C, strain energy, where here strain energy is taken as integration 0 to y deflection P into dy, strain energy produced by load P. So we are taking P into deflection. So potential energy formulation, will go with formulation of potential energy. The stresses are related to strains, and strains in turn are related to displacement. So in potential energy, stresses are related to strains, and strains are related to displacement. This give rise to second order potential differential equation. Where stresses are related to strains and strains are related to displacement. So these are giving rise to second order PDEs. The solution of system of such equation is difficult to obtain for general problems. For problems involving complex geometries with general boundary and loading conditions, we need to formulate and find solutions. The two approximate methods to obtain solutions such problems are potential energy method and variational methods. So total potential energy for single force member configuration in deflected equilibrium state. where y is deflection and p is load. So to internal strain energy is divided by u and dy, and v and py is showing the potential energy of external applied loads. So u and dy is giving the internal strain energy, and v and py is giving the potential energy of external applied loads. So the formula is total potential energy equals to strain plus uh, internal strain energy plus external potential energy equals to integration of 0 to y means deflection, and p into dy minus py, where total potential energy equals to u plus v, where v equals to summation r equals to 1 to n v suffix r is radius, equals to summation r equals to 1 to n minus pr delta r. So r is potential energy of all loads, delta r is a potential energy of all loads. So a system consisting of loads p1, p2 and pn producing corresponding displacements delta 1, delta 2, delta n in the direction of loads. So finally we'll get the by solving all this we'll get the equation as total potential energy equals to u plus summation r equals to 1 to n minus pr delta r. So we'll go with, now here we'll go with minimum total potential energy. What is minimum total potential energy? The minimum total potential energy principle is a fundamental concept used in physics and engineering. It dictates that at low temperatures a structure or body shall deform or displace to a position that minimizes the total potential energy, with the lost potential energy being converted into kinetic energy. So the minimum total potential energy is a fundamental concept used in physics and engineering. It detects that at low temperature a structure or body should deform or displace to a position that minimizes the total potential energy, with the lost potential energy being converted into kinetic energy, specifically heat. In the complementary energy method, we assume virtual forces going through real displacements in the direction of the displacement intended. Now we assume real forces go through virtual displacement that are in direction of forces. So potential energy method. For conservative systems, the work potential is independent of the path taken. This means that if the system is displaced of the path taken, this means that if the system is displaced from given configuration and brought back to it, then the force do zero work irrespective of the path taken. So the potential energy method is it is used for conservative systems. The work potential energy is independent of path taken. The potential work is independent of path taken, and it means that system is displaced from given configuration and brought back to it, then the forces do zero work irrespective of the path taken. The total potential energy method. In the spring or mass system shown in its unstrained position, we normally define the potential energy of the mass as a product of its weight mg and its height h. Above some this mg is weight is denoted by mg and height is denoted by h above some arbitrarily fixed datum. In other words, it possesses energy by virtue of its position. After deflection to an equilibrium state, the mass has lost an amount of potential energy equal to mgy. Thus, we may associate reflection with a loss of potential energy. Alternatively, We may argue that the gravitational force acting on the mass does work during its displacement, resulting in a loss of energy. Applying this reasoning to the elastic system of figure 1. Elastic system, and assuming that the potential energy of the system is zero in the unloaded state, then the loss of potential energy of the load P as it produces a deflection Y is P1. Here is the examples. Y P M is mass, P is load, Y is deflection, H is height. It has shown in the spring loaded systems and normal loaded systems. So figure 1, potential energy of a spring mass system, and figure B, loss in potential energy due to change in position. Thus the potential energy V of P in the deflected equilibrium state is given by V equals to minus Py. Then minus is using because of deflection. Here in the formula, minus is using because of deflection. We now define the total potential energy of a system in its deflected equilibrium state as a sum of its internal or strain energy and the potential energy of the applied external forces. Hence, for the single member force configuration of figure 1. So here is the formula. This formula just I have defined about the formula. The sum of total internal strain, sum of its internal or strain energy of the potential energy of the applied external forces. Hence, for the single member force configuration, this is for the single member force configuration. This total potential energy formula is for single member force configuration. For a general system consisting loads P1, P2, Pn producing corresponding displacements, that is displacement in the direction of loads delta 1, delta 2, delta n, the potential energy of all the loads is V equals to summation r equals to 1 to n Vr equals to summation r equals to 1 to n minus Pr into delta r. Minus is used for deflection because of deflection. Again the formula is shown here. So what is the stationary value? Delta into u minus summation r equals to 1 to n Pr delta r equals to 0. Above equation means variation of total potential energy of system is 0. So the above equation means that total potential energy of a system is 0. This quantity does not vary when a virtual displacements are applied. The total potential energy of this system is constant and is always minimum. So the total potential energy of a system is constant and it will be always minimum. Always the total potential energy of a system will be minimum, and this quantity does not vary when a virtual displacement is applied. The principle of the stationary value of the total potential energy. Let us assume here we are calculating the potential energy of an elastic system. So let's assume an elastic system in equilibrium under real applied forces P1, P2 and Pn goes through virtual displacement. You can see in the figure delta 1 plus delta 2 up to so on delta n in the direction of load. Virtual work done by force is summation r equals to 1 Pr delta r minus delta u. U is the strain, delta is deflection. So here we can get the formula of total potential energy system is 0. The principle of stationary value of the total potential energy. So definition of is this definition is the total potential energy of an elastic system has a stationary value for all small displacements when the system is in equilibrium. The equilibrium is stable if the stationary value is minimum. So the equilibrium is stable if the stationary value is minimum. If the stationary value is maximum, then it is not in equilibrium. The principle can be used for approximate solution of structures. Here is an example of TPE showing a graph qualitative demonstration. So the x-axis is taken as strain energy and y-axis is taken as sum of strain plus internal plus external energies equals to f of height. So here we have taken at a point it is unstable equilibrium, and at b point it means if you trigger particle, its total potential energy does not change. It is balanced equilibrium. So the formula we can take is delta into u plus u by dou u equals to 0. And at a or b or c different these points are different equilibrium states of particles. So at c points it is at neutral equilibrium. H shows the height of the so the principle of the stationary value of the TPE may be stated as follows. The potential energy of an elastic system has a stationary value for all same displacements when the system is in equilibrium. Further, the equilibrium is stable if the stationary value is minimum. So this principle may often be used in the approximate analysis of structures where an exact analysis does not exist. When suppose that the displaced form of the beam is known and must be assumed. This approach is called the Rayleigh-Ritz method. So in this method, often a displayed form of the structure is unknown. A displaced form is assumed for the structure, also called Rayleigh-Ritz or simply Ritz method. So Ritz developed the method proposed by Rayleigh. So Ritz method is a derivative of stationary value of potential energy. By minimizing the potential energy, unknowns can be obtained. This method is very useful when exact solutions are not known. Let's see it in some examples. Example, consider the simplest model of an elastic structure, that is a mass suspended by a linear spring. Find the static equilibrium position of the mass when a force F is applied. So deflection is denoted by delta, and x is the distance, and we have to find the mass when the force is applied. So here we can take the strain, we can take as half into kx square, where v equals to minus force into x, and the total here we are taking the formula as v equals to u half kx square minus fx, where delta into u plus v by delta x equals to 0. F equals to kx equilibrium, F equals to k delta. So delta square into u plus v by dou x square equals to k. We'll get the final solution. So it is the second derivative is positive, meaning the function or total potential energy is minimum at the equilibrium. This equation shows the second derivative is positive, meaning the function or total potential energy is minimum at the equilibrium. So this is all about total potential energy. Thank you.